So as I was saying, the the other time, the sorry to disturb you. When we were calculating the displacement, I told you that the main difference between the slope and the displacement is that in the slope it's just the m over the integral of from a to b of the m over ei diagram, that is the bending moment diagram. However, for displacement, it has the distance s, which is the like the centroid multiplied by the m over ei. That's the major difference between the two. Now, for this particular case that we are treating, I I told us that the m over ei of this particular shape here is this, while the one for this particular shape here is this. So to treat the, we are looking for the displacement. Now I told us that the displacement is we'll be multiplying with m over ei with the centroidal distance. Unlike if it is slope, we'll just be doing the moment, taking the moment diagram alone, integration of the moment, bending moment diagram. Now for this particular one, we, since we already know, okay, for this place the bending moment here is 250, the bending moment here is 500. However, this shape is rectangle, right? So definitely the centroid is just around this area, while for this particular one the centroid is around this corner here. Now let us look at the calculation. The displacement of b from reference point a will be equals to this bending moment here for times this distance 2 first, because that's times this distance 2, then multiplied by the centroidal distance from here to here, that's 1. That's for this particular case here. Now this 250, that's the bending moment for the position b. This is for the 2 meters, and this is the 1 meter centroid. You know, from here to here is 1, from here to here is 1 meter. So now, however, since we have the other consideration, the for the, just substitute whatever you have, the ei, that one is given already. The e is 200 times 10 to the power of 9, I is 4 times 10 to the power of 6. Just substitute those one, you get your displacement at b. However, for this particular displacement at c, which is to a, c to from distance of a. Now what we're going to do in this particular case is that we take the bending moment of this one times this distance, then times the centroidal distance of 2 plus the other one the other one, which is the short length, times, that's bending moment of it, times the whole full one first, then times the centroidal distance, half of this, which is 0.5. So if we consider this, this is what we're going to have for this. Just substitute the value of this, the m over ei diagram. The area covered by the moment is this moment times this span, then multiplied by the centroidal distance. But because it's from we are referencing c, and that particular distance does not cover to the end, so it's covered up to the 2. Now for this other one, we take 1200 times 1, then up to its own centroidal distance of this. So by the time we sum these two together, we have this. Now since both answers are positive, they indicate that point b and c, they lie above the tangent at a. Now let us look at another wonderful experience that is not cantilever beam, which is just a simply supported beam. Now this particular one, if you draw the bending moment diagram, everybody can draw this. This is just, you can say this is uniformly distributed, let me say symmetrical. You can say this one is moment is around 60 from here to here, 20 times 6. You can draw the bending moment for this particular one. However, if we have this bending moment here, we have this our bending moment diagram. Let's say this is our bending moment diagram. We want to determine the slope at c, the slope at this particular point c. And in the diagram here, we have this is the target at c, this is target at d. Then you can see what we have here: target at c and target at d to c. Now since the loading is applied symmetrically to the beam, the elastic curve is symmetric as shown here, and we are required to find the slope at c. So this can easily be done realizing that the tangent at d is horizontal, and therefore by construction, angle theta d, which is to c, between tan c and tan d is equal to this, that is this one is equal to this. Now to do that, all we just need to do is just the same principle that we did the other time. This is the area we are making reference to, that is we want to get the displacement, the slope with respect to this d. So all we just need to do is, this is the area we need in this diagram. However, if you look at this diagram very well, we can see it's two it's a triangle and a it is a triangle and a rectangle here. So what we're going to do is we're going to treat it as such. Now let's treat the first one, which is the rectangle first. It's 30, this height is 30 times 3, which is what we have here, plus, now let us treat this other one. Now area of a triangle is half base times height, so we're going to say half times this base is 3 times this height. However, to get this height, we remove this from this, which is what we have here, 60 minus this, then we have this calculation. Once we sum it together, we have this. Now by the time we put our EI value, this is what we are going to have here.